Okay, hello everyone. So thank you for inviting me to this reading group, or in this particular case, thank you for making me come to this reading group. No, just kidding. More seriously, I'm going to talk about. I'm going to make sort of an introductory, not really a course, but really a presentation about mean field theory aimed at non-specialists. Because this stems from a talk I gave about a year ago at this reading group, which was my first talk since the beginning of my PhD, and which was honestly not very good. I skipped some important parts. It was not really aimed at a wider audience. So this talk stems in part from discussions with Marco, and aims at correcting that and presenting a sort of an introductory course to mean field theory for people who don't know mean field theory at all. So there's going to be some technicalities, of course, but well, I've tried to make it so that there is no really need to know anything special. I mean, in sort of prerequisites. I don't think there are really any specific ones. So first, I'm going to introduce what mean field theory is, and then present the main mathematical questions that people ask themselves usually when working with mean field models. And this will be the main object of the talk, which is to present the heart of the theory. So what is mean field theory? Mean field theory is a particular case of studying the dynamics of a system of interacting particles. So what we're interested in fundamentally is the evolution in time of a system of interacting particles. So in this case, particles has a very, very wide meaning, because it can be, well, actual physical particles, or it can be people in social dynamics. It can be players in game theory. It can be cues, and so you can see each, like it's basically the object of interest, and it can represent many different things depending on the context. And this is, in a way, the main interest in mean field theory, is that, well, this is an extremely general object, and so a lot of problems from applied mathematics can be modeled in such a fashion. And because of that, since we'll be able to construct mean field models on such situations, it makes mean field theory a very versatile tool, which sort of justifies the interest that one can have in it. So it has many applications. So basically, the idea behind mean field theory is to make sort of the bridge between a microscopic approach and a macroscopic approach, which is a more statistical approach. I'll discuss both in this talk. So the idea is that we have a system of n interacting particles, and what we want to do is to study the behavior in time of the system. So what we do is that we write out equations, which often will be stochastic differential equations, to describe the behavior of the system. So, by the way, I didn't say it, but of course, if there's something that is not clear, if you want to ask a question or anything like that, feel free to interrupt me. There's no problem at all. But I don't see the chat, so please put on your mic and ask the question, of course. So, when you're describing the behavior of the system, what you're doing is a microscopic approach, because you're looking at the particles themselves. And what you want to do is, well, describe how they evolve in time. So one example that's quite general and at the same time very simple is the one I give in this slide. And if you're not familiar with the stochastic differential equations, here the stochastic part is limited to a very contained process. So basically here, what we say is that so xkn represents the state of the particle k amongst n particles, and at time t, which is denoted either this way, or sometimes we put the t as an underscore. So what we say is that the behavior of the system, of the kth particle of the system at time t, is equal to the initial behavior, which is, of course, the initial conditions over here, plus some noise, which is the Brownian motion. So Bm is Brownian motion. W, so we have n Brownian, independent Brownian motions. So for those not really familiar with Brownian motions, I don't think that's really, I don't know if it's anyone here, but it's basically just a continuous process that behaves like a sort of with small oscillations. So it's kind of a non-differentiable noise. So this is where the stochastic part comes from. This is the randomness inside this model. So this is just some noise. Plus, so you have an initial condition, you have some noise, and you have interactions between the particles, because as we've mentioned at the beginning, we're interested in a system of interacting particles. So this integral term is just a modelization of the interactions of the particles inside the system from and we are summing all the interactions from time 0 to time t. So so of course, as you can see, so we're basically describing what happens in the system. So all the how should I put it? The crux of the problem is the interactions that happen inside the system, because that's the interesting part. So here we have a lot of basically in this diffusive model where the randomness is represented by a Brownian motion, so Brownian noise. The crux of the matter comes from representing the interactions between the particles. So to do that, this is a relatively standard mean field term of interactions. So we say that the interactions that the particle K sees from all over the system is represented by a term here of a mean of all the interactions that happen all over the system. So B is a globally Lipschitz function. So what you can see B as is basically the function that tells you how two particles interact. So you have two arguments, and B of x and y is the interaction between x and y. So in case if you're looking at physical particles, you can imagine this has some sort of attractive force or something like that. If you're looking at I don't know, neurons in neuroscience, you can imagine that it's some kind of electrical input from between neurons K and J, something like that. So depending on your situation, you model the interactions to fit your situation. So and so this particular equation, this equation 1, is a relatively general equation, and it describes a relatively general type of interactions. And 1 over n, which is sort of the weight of the interactions. So it's a sort of a normalization. So you have sort of an empirical mean, as you can see, of all the interactions that happen inside the system. Okay, so far so good. Okay. So this is the microscopic approach.
Michel?
Yes.
Just a small question. Will you give some example of function B on a
yes.
use case?
So if you see my the plan of the outline of the talk, the second part, convergence in a toy model. The toy model itself is the simplest possible example of function B. So all the actual calculations will be done with a very simple function B.
Okay.
And the idea is that it can be generalized to any function B. But the idea, you can imagine B as being simply x minus y, for instance. That's the example in the convergence in the toy model. So of course you can imagine something more complicated, like exponential kernel.
If it's a difference, what does it mean in terms of model?
Well, in terms of model, I'll talk about this in later. But basically, you will be able to see that that will basically model some kind of exponential convergence to a sort of a mean state.
Okay. Okay. Thank you.
It will actually be clearer later on with a slightly different form of it, the same equation.
Okay.
Okay. So this was a presentation of the microscopic approach. So this is I've just rewritten the same equation again, just because to keep it to have the remarks at the same time that we have the equation. So if you remove the noise, I was kind of I kind of talked about this earlier. If you remove the noise, you just get a set of ordinary differential equations. So all the randomness comes from the Brownian noise term over here, and these equations are well posed because because B is very strong tool, which is the stochastic Cauchy-Lipschitz theorem, which is basically just a version of the standard Cauchy-Lipschitz theorem, but for stochastic differential equations, which gives us both existence of the solutions to this set of equations, and you actually get a uniqueness of the solutions in the sense of the trajectories. So you only have, given an initial condition, you have only one trajectory that solves these equations. So the good points of these equations is that it's a very good modelization. Why? Because you're actually describing what happens in the network. So your network of with your n nodes, you've just said what happens in it. So of course it's going to be a very good description. But the hard part is because of the interactions term is pretty hard to compute, because you have to take the mean, you have to take the interactions of all over the system in order to get the behavior of particle k. You need to compute, you know, basically the behavior of all the system at all times previous to t to know what happens at time t for one particle. So of course you have to sort of strike a balance between a good modelization and to be able to do computations to be able to compute elements on here, because they're pretty complex equations. So the idea behind mean field theory is to sort of take a simplified version of the same situation, as to speak, but to simplify the expressions by taking some kind of scaling to get simpler equations. So the most classical scaling, which is what I call the macroscopic approach, is to describe the statistical distribution of the particles. That is to consider that you have an infinite number of particles that interact in a weak fashion with one another. So you still have a sort of a symmetry that was present in the previous equations. But the idea is to basically consider that one of the parameters goes to infinity, so we don't have to bother about it in some sense whatsoever. And here, yeah, and so here are basically in some sense, the limit equations, in the sense that here we look at what do we think that the equation would look like if the number n of particles went to infinity. So if you look at the previous equation here we have some kind of empirical mean. So the assumption is that when n goes to infinity, here by a sort of a lot of large numbers result, we can hope that this mean converges to some kind of mathematical expectation, to the expectation of the function b of x. So we pose actually stochastic differential equations with exactly that. So we replace, all we do is that we replace the interaction by the interaction we imagine that happens at the limit. So so here we replace the term of empirical mean by a theoretical mean, and we take the integral by so we take the mean of on the law of the solution of the stochastic differential equation. So in some sense, this is much simpler, because here it no longer depends on the order of the particles. That's the main reason why we're interested in such a model. But it's also more complex, because here you have a dependence of the law of x. Basically x at time t depends on its law. So this is what we call a nonlinearity, because, well, the process depends on itself in this way, and because of that, so the law of xk depends on the law of xk at a different time. So because of that, you obtain nonlinear SDEs, nonlinear stochastic differential equations. So this is a few remarks, which is basically what I've already said orally. So this is what sometimes is called the thermodynamic limit in certain circumstances. But basically, what we do is we consider the situation where where there's an infinite number of particles, and the heuristic is that the new stochastic differential equations are what we intuitively believe the limit to be when the number of particles goes to infinity. And the advantage is that the equations are in some sense much simpler because they don't depend on each other anymore. So it's much simpler to compute. So because you have asymptotic independence in between the particles, but they're no longer linear. And of course, there's compared to the initial model, since we've taken a simplification by making the number of particles goes to infinity, there's some information that is lost compared to the initial model. So in particular, the correlations between the particles, because all the particles become asymptotically independent, or any effects that might be due to the geometry of the initial model. For example, due to the finite size, or just if you want to model some kind of spatial component, just by doing what I did, you lose that by taking the mean field limit, because what I did is called taking the mean field limit. So why is it called the mean field? So this is the next slide.
Michel,
yes.
This is Sanket. So
yes.
Can I ask one question? Yeah.
Yes, of
so
course,
in equation two, you had x bar. What does exactly x bar mean here, or is it just a different notation?
It's just a different notation because later it will make sense to call it x bar because it's kind of the limit of x. So it's basically at this point we could use any notation, but later on, since we'll be looking at both the microscopic and macroscopic equations at the same time, and we'll be linking them very closely, it makes sense to use a similar notation. Okay. So this is the reason. I hope this clarifies it. So this is where I hope this actually makes things clearer later on. So I was talking about why do we call this mean field actually, is because the first equation, the one, the microscopic one, we can rewrite it in terms of its empirical mean measure. So what we can say, you say that the term of interactions is exactly the same as this one. It's just we're just rewriting it in terms of what we call the empirical mean measure, which is precisely this. So the empirical mean measure is the empirical mean of the measures of the positions of the different points. So R is basically the time. So it's the time parameter. So we're putting a weight at all the state variables at time R in this case. So and what we're interested in, if you compare this equation to the limit one, we're interested in showing the convergence of the empirical mean measure when the parameter of the number of particles goes to infinity. So if you look at the previous equation 2, just at the limit, all we've done here is replaced the empirical mean with this measure. So now this is the main intuition behind the term mean field, is that what we're interested in is the convergence of a empirical mean measure. So we're interested in the convergence of so we've got some kind of convergence of measures. Okay, this is clear for everyone. And so if there is convergence of this empirical measure, from what we've seen, then there is asymptotic independence, and this I'm just introducing the vocabulary here. This convergence of this empirical measure to a certain constant measure is called propagation of chaos. I'll factually explain later on why this is called in this way, but the main idea is that basically imagine that your initial conditions are in some sense independent. So the idea is that these dynamics, if there is a convergence of this empirical measure, will preserve this independence at infinity because we have asymptotic independence. So this idea of preserving independence, which can be seen as preserving the chaos, or some inside the system, is the reason this is called propagation of chaos. Is that clear? And if it's not, please feel free to ask questions. And of course, oh, not of course, but another interesting point that is seen when you write it in terms of its empirical measure is that the law of the random vector of all the state variables. So if you look at the law of this, it's invariant by permutation. So basically, because all the particles can be written, the behavior of all the particles at time t can be written in terms of the behavior of its empirical measure. So of course, since this is symmetrical in all the particles of the system, you can see that you have exchangeability. That is, that if you make a permutation of all your particles, you still get the same law. So this is another reason why mean fields are attractive, is that the models themselves have this inherent symmetry, so this exchangeability, what we call exchangeability, that that simplifies a lot of the calculations, and this is one of the main arguments for studying mean field models. So of course, the downside to this is, of course, if your initial model is extremely non-symmetrical, well, the mean field model is not going to give you many, it's not going to give you a lot of information about your initial model. Hope this is clear.
Can I ask a question?
Yes, of course.
So there is this move from 2 to 3.
From 1 to 3. From 1 to 3.
Well, because you had the measure mu, which was
yes, okay.
the measure which was describing the distribution of x.
Yes.
That should be the true measure, right?
So the idea is that here it is the true measure in the limit model. So this is this equation. It describes the system at the limit when the number of particles went to infinity.
So I wonder, is it possible that, for example, the empirical measure, the E that you use later on,
yes,
would converge to a different mu that is not?
Yes. So yeah, the idea is that the idea is that if the idea of the mean field theory is to see if you can associate a macroscopic model to your microscopic model. So to see what does the empirical mean converge to, if it converges. So the idea is that you sort of fit the limit equation to the limit of this empirical mean.
Okay.
Is that clear?
Yes, I'm just asking. Yes. Okay. Yeah.
Okay. So yeah, so when we're interested, what I'm saying in this slide is that the problem we're interested in can be rewritten as what does this converge when n goes to infinity, and if it does, what does it converge to? Okay.
Mm-hmm. Okay.
So what kind of results do we have in mean field theory? There are two results. Two main types of results. Of course, there can be others. The first is that the equations which are at the limit, so the equations 2, which are at the macroscopic limit, you have to show that they're well posed, because as I've mentioned previously, they're non-linear. So the most basic theorems for stochastic differential equations don't apply to them because they have this non-linearity. So we have to show that there exists indeed a solution to those equations, and that the solution is unique. So this is what well-posedness means. And so, and of course, the other type of results. The first one is kind of, in some sense, more technical, but the one that is perhaps more interesting is that you can when you look at the convergence. Well, sometimes you have the convergence in probability or the weak convergence of the empirical mean measure on the space of probability measures on the space of trajectories. So because So what the empirical mean here, on what is it? It's a measure. On what is it a measure? It's a measure on the space of trajectories. So the convergence that you want to take place of this empirical mean must take place in the space of probability measures on the space of trajectories. So in this talk, so this has been a sort of a general introduction to the aim of this talk is to discuss, not without going into technicalities, the general techniques used to prove the first type of results, that is the well-posedness of the stochastic differential equations, and mainly to present a way on a simple toy model to prove the convergence of 1 to 2 using so-called coupling techniques. So this will be the main part of the talk, and the first part is more is just to present the main ideas of it. So to show the well-posedness of the limit as these, there are basically two main techniques, which are kind of the same techniques but in different worlds. The first technique is more a probabilistic approach, and the second is more analytical, working with the underlying, sort of looking at the underlying partial differential equations, which are something I won't discuss here at all. So I'm just interested in describing the probabilistic approach to prove the well-posedness of the limit stochastic differential equations. So what does the probabilistic approach entail? First, you define the right distance on the space you're interested in. And by right distance, I mean a distance that is well suited to showing the convergence on the space you're interested in, which will of course depend on the type of trajectories you're working with. Here, all the equations I've introduced, all the solutions are continuous. So here we're working on the space of continuous functions. So there will be a specific distance associated with that space. Of course, if you work in a different context where I don't know, you're working with piecewise continuous functions, for instance, you will have a different distance to introduce. Then, so the probabilistic approach entails introducing a function on the space that associates to a measure the law of the solution to a linearized version of the stochastic differential equation. And so I'll get into more detail on this in the next slide. And then you show that the function phi has a unique point, and that this fixed point is the solution to your stochastic differential equation, and since it has a unique fixed point, you will have only one. You will have both existence and uniqueness of the solution. So this is a very very general terms. It will be more clear, I think, on actually with the example that I'm going to give here. So the distance was, so this is I defined briefly the distance that we introduce. It's kind of a barbaric term if you're not really familiar with it. It's called the Wasserstein distance. So it's not really that important to understand exactly what it entails, but basically it's a measure. All you have to understand if you're not really familiar with this is that it's a distance on the space of probability measures on continuous functions, and that basically it becomes a complete metric space with this measure. That is, all Cauchy sequences on this space will converge under this distance. And an interesting property, which is more anecdotal here than anything, that is this Wasserstein distance is non-decreasing in T. So this is not really, it's not that important, but it's an interesting observation. So all you have to see is that it's the distance between two probability measures on the space of continuous functions from bounded interval 0t into Rn. Okay. What we introduce here is what I've mentioned previously, the linearized stochastic differential equation. So you have a function phi that goes from the space of probability measure on continuous functions to itself, and so to each measure it associates another measure, which is the law of the solution of this following differential equation. Okay, so this is we just pose this stochastic differential equations, and we say we'll just pose a function that to a measure associates the law of the solution to this differential equation. So as you can see, so compared to the original stochastic differential equation that we're studying, for which we want to prove existence and uniqueness of the solution, you can see that here they're basically the same, but for this term here, for the measure itself. So the idea is that if here the function phi has a fixed point, this fixed point by construction will be a solution to this stochastic differential equation. Because basically, if it's a fixed point, phi of m is going to be the law of this of x of s of z of s here. Okay. So the idea is that if you can prove that the function phi has a unique fixed point, the fixed point will indeed be the solution to the original stochastic differential equation. So the main result that I'm not going to go into detail, I'm just going to give the idea of the proof, is that this function has indeed a unique fixed point. And so the idea is that using Grunwald's lemma, you can give a bound for the Wasserstein distance of phi of mu and phi of nu using the Wasserstein distances of mu and nu. And basically the idea is that you can iterate the reasoning. So you can show a similar bound for iteration of phi. So if you look at the iteration of phi, you will have that the phi ends will be a Cauchy sequence. Since we have a Cauchy sequence in a complete metric space, this sequence will converge. So this will have a limit, and the limit will be a fixed point of phi. So this is so I'm going. So this is mainly to give the main ideas of the proofs. It's just to kind of for completeness' sake, because as I mentioned, my goal here is to present like the main results that people study in mean field theory. And so there are two kinds. So the well-posedness of the limit equations and the convergence in a toy model. So what I've presented here is the main method to prove the well-posedness of the limit stochastic differential equations in this context. So in the context of mean fields. So this is so it's a relatively general. So these are relatively general ideas. But if you, in some sense, if you're looking from from applications point of view, you can sort of this less interesting because we can sort of leave this to the theorists. You can there's relatively standard techniques to show that these limit stochastic differential equations are well posed, and you can only be interested in the second part, which I think is actually easier to understand than this part. So this hasn't been clear, this part hasn't been clear, now the second part about the convergence in the toy model will hopefully be much easier actually. So from the consequence from the previous result I mentioned is the existence and uniqueness, so the well-posedness of the limit stochastic differential equations. So now we've sort of answered the first question of mean field theory. Now we're interested in answering the second one, which is I think the one that contains the most ideas that you can understand from an intuitive point of view, because the first part is kind of technical. So here, as I've mentioned previously, we're to simplify calculations just to see what happens. We're going to consider the initial model with the function b of xy equals to x minus y. So in this case, the first term gets out of the empirical sum because it's all the same. And so what you see is that your equations, what do they represent? So you still have the initial conditions, you still have some noise, some random noise. And what you have here is simply a differential equation where you basically have the difference between the particle itself and the mean position of the particles. So if you disregard the noise, all that you have here is an exponential convergence to the mean position of the particles. And you can solve it explicitly. There's an explicit solution. And I'll briefly mention this in the next I think slide. And as the here is linear, so it's very easy. It's pretty easy. So that's why we call it a toy model. But the idea is that this simplified model, we can be able to do calculations that you can also do with the function b, but with the general function b, but that the calculations will be much more complex. So that's where we restrain ourselves to this toy model on which you can follow what is happening more easily. So basically here you have exponential convergence to the mean position of particles plus some noise. Okay, is this clear, Marco, for instance, because he asked the question in the beginning?
Yes.
Okay.
This slide, yes, the previous one,
yes,
it was complicated to me, but
yeah,
this one is okay.
Yeah, the previous ones were more like I felt I had to present them because there's one of the main questions associated to mean field theory. But I think for a non-specialist, the first part was hard to follow. I'm aware of that. I hope this part is aimed at more for everyone.
Excuse me, Michel, I have maybe a stupid question, but I have the feeling that here you're considering a repulsive force because the derivative of xk is essentially the vector xk minus the center of gravity.
Minus is needed.
Yeah, I think that there should be a minus.
You see, here you mean?
Yes.
Maybe. Yes,
because
I think yes.
I had exactly the same question. Yes, here you have an explosion, and if you want to have an implosion, yes, you've got to have minus.
Yeah. You're right. Yeah, sorry. Yeah,
Okay,
here we have yeah. But if of course it will change nothing in the calculations. You can imagine all of what follows has a minus here. Okay, but since we'll be taking normally this won't change anything later on. Yes, thank you. Yes, thank you for the remark. I'll correct that. And so so since there was a plus here, though there'll be a plus in everything that follows, but everything works with a minus here too. But the limit process now, intuitively, what we have here is that this convergence to the expectation. So you just the limit process will just verify the following stochastic differential equation with this replaced by the expectations. And since because of the symmetry of the system, this is the expectation of the same particle. So as you can see, since because of this term, you still have a dependence of xk on itself in a nonlinear form. So there's still nonlinearity on the limits. We call this when they depend on the expectation Makin class of nonlinearity. But an interesting point that now there is invariance in law for all k. And what I have previously mentioned, that if you call mu zero the law at time zero, if there's a finite first moment, you can rewrite this as a linear SDE with an explicit solution, which is called an Ornstein-Uhlenbeck process. So I'm not going to go into detail on this, but the idea is that this can be solved explicitly, and you can have an explicit solution for xk of t. X overline xk of t here. So and you can write it out. It's not particularly complex, just with some exponentials. But listen, okay. So now, what do we know? What I remind you that what we want to do is to prove a link between the two system of stochastic differential equations, the one at the limit and the microscopic one before the limit. And we want to show the convergence of the first one of the microscopic one to the macroscopic one. So to do that, the main idea is that, well, what we want to do is to bound the difference between the two, right? So if you want to bound the difference between the two, the problem is that you have some randomness in the difference. If you look at the two equations here, 6 and 5. So if you take the difference, there's some randomness in, of course, in the law of the initial in the law of the initial conditions, and there's some randomness in the Brownian motions. So the idea is to do what's called a coupling. What is a coupling? Is basically to construct the process of all the processes on the same probability space with the same randomness. So since it's the same, so basically what we're doing with coupling, so we're linking the randomness in the two equations. So the idea is that the two equations will have the same inherent randomness. So how we do that is that the probability space that we consider here is as follows. We endow it with a measure on the initial conditions and on the Brownian motion. So the WQ is the Wiener measure, which basically is the measure of the IID Brownian motions. So which we call here BKT. So BKT is the Brownian motion of particle K at time t. And this is the same as this. So as you can see, this is the main reason for using the overline. So basically, as you can see, this is really the same as this, basically, but for but for the term of interactions that you replace with its supposed limit term. Okay, is this coupling quite clear? So you have the same. Now you have the same initial conditions and the same Brownian motions because you're constructing your processes on the same probability space. Okay.
Just to see if I get it right, can I imagine that with a coupling, the initial condition and the noise are now deterministic, and so we will solve this in a deterministic way, and afterwards we'll use the coupling to prove the convergence?
Not exactly, but the idea is that we'll be able. The idea is since we're looking at the convergence, we're looking to measure the distance, so the difference between the two processes. And so by making it so that the randomness is the same, the difference between the two will be zero. So you have no longer, you have determinist. So you have in some sense deterministic equations for the difference. Okay.
Okay.
Does this answer your question?
Yep.
Another question.
Okay. Yes.
What is the range of K here?
K goes from 1 to n. But the idea is you have sort of so for the limit you can define it for all k here, but so you here k goes from 1 to n, and here it goes for you have an equation that you can define for all k, but it's the same equation for any k. So you can take the difference between, you can just look at the ones for k from 1 to some kind of fixed n that you. So it's okay. So you can sort of fix a range and then make a parameter go to infinity and look at the difference for k's in the same range. Okay. So what do we do? As I've been saying. So what is the result that we have? So with what we're going to show is this is the following convergence theorem, where we're going to say that the difference between the two solutions to the equations is bounded, and that there is bounded by something that goes in 1 over square root of n. And so we even have the speed of convergence. So this goes to the difference between the difference between the two goes to 0, and you even have the speed of convergence here. So all you have to do under the we make the assumption that at the initial conditions the measure has a finite second moment, which we call 0, and just from that we can show that for all finite t, for all k in between 1 and n, we have the following. So when n goes to infinity, if you make n go to infinity, the difference will go to 0. Okay, so we're actually going to prove this almost completely. There's just one step that I'm going to assume something. But so, and again, I won't go into too much detail, but the intuition behind the proof is that since we are going to show an exponential bound, we're going to use Grunwald's lemma, which is one of the main tools for this kind of problems, which is Grunwald's lemma goes as follows. It basically says that if you have a differential inequality under some pretty general assumptions, you can sort of integrate under the inequality. So here so what it's saying is, if you had an inequality here, this u of t would, the solution to this differential equation would be this. And so what we're saying is that under hypotheses on the terms here, well, you can, it's still true even with the inequality. So that's how I see the intuition behind Grunwald's lemma. So assume that so this is a simple version that can be generalized to a much more general setting. So assume that the functions u are non-negative and continuous, that the function b that you have here is also non-negative and continuous. Here you have a non-negative constant. You can even generalize this to a non-negative continuous function. And so if you have the integral inequality, then you have a bound for u that does not depend on u anymore. That's the main interest for us. So the intuition that if you can bound the difference here, if you can bound this by something like this, then you're going to get a bound like this. And if your a is in 1 over square root of n, then you'll get the desired result. And so this is exactly what we'll do. So what we do by the coupling, we can, when we take the difference of the two, we're just taking the difference of the two equations, and we can bound it like this, because thanks to the coupling, which was the main reason for introducing that argument, there is no longer any term of the initial conditions and no longer a term of the Brownian motion. So the by coupling on the inherent randomness of the system, there is no longer any randomness involved. Well, in some sense. Of course, the processes itself are still random because there's a hidden Brownian, there's a hidden randomness, of course, inside here. But the idea is that in this difference, there is no longer any Brownian difference of Brownian motions that we could not bound, which did not go to 0. So now the idea is that we can bound all of the terms. So how do we do that? So first of all, because we're interested in bounding this, because to sort of to get a sort of a normalized version of the difference. What we do is, well, we just rewrite by taking the expectation equation above. We can rewrite this inequality in terms of the function delta. So we just say that this can be bounded by we can bound the delta of t by 2 delta of s plus this term, which corresponds to this term. Okay. So how do we bound this term? So to bound this particular term, what we can see is that here you have the expectation of n of a centered random variables. So here you have the variance of you basically have the variance. So what we're saying here is that what we're looking at is the expectation of centered random variables. So what can we say from this? So yeah, this is what I've been saying. So if you look at dn of t, which is the term that we have to bound, this is the first moment mean of an empirical mean of centered independent random variables, because at the here we only have the limit process, so all the xj's are independent. So we have the empirical mean of centered independent random variables. So we can use the Cauchy-Schwarz inequality to say that this is bounded by the variance of just one of the terms with a 1 over square root of n in front of it. So all that we have to do now is bound this variance, because once we have done this, we'll be exactly in the situation of the Grunwald's lemma that I've described. We'll have here 1 over square root of n times the constant plus something that depends on the function itself. Just here b will be equal to 2. Okay, so here you have exactly that. If you can bound this by 1 over square root of n times constant, you get by Grunwald's lemma exactly what we want. So how do we bound the variance? Well, actually this is the part that I'll skip because it's it's not very interesting, but it's actually very easy. So recall that that this is the solution of a stochastic differential equation with an explicit solution. This is what I've mentioned previously. You can solve x1 of t and get an explicit solution for the expression of x1. So all we do is take the variance of that explicit solution, and by taking that, I won't do it because it's just a technical calculation, but you immediately get that it's bounded by mu zero, which is, if you recall, the variance of the second moment at time 0 plus a constant which is equal to 1/2. Okay, so you bound this by mu 0 plus 1/2. And finally, what do we have? We have exactly what we wanted, which is that you get delta of t, which is bounded by 2 times delta of s plus a term which has a 1 over square root of n in front of it. So you apply Grunwald's lemma, and Grunwald's lemma gives you exactly this, because this is delta of t. So you get the square root of delta of t is less than or equal to this. And since so we've proven the convergence on the toy model using a coupling argument, which is it. So you can say a few more things. You can say that that the bound gives you a control of the Wasserstein distance. So 9 is this. So this bound gives you actually. I won't go into detail here, but you can show that this gives you a control on the bound of the Wasserstein distance, which, as if you recall, is a distance on the space of the laws of continuous on this distance on the space of measures on the space of continuous trajectories. So you have a control for the Wasserstein distance between the laws of this and this, and so the Wasserstein distance gives you so since it gives you a complete metric space, it also this implies the convergence of the law of x, k, and t to the law of the limit solution. So you have this convergence in the space of measures on the continuous trajectories. So now we have shown the convergence of what we wanted, so the microscopic model to the macroscopic model. And it's actually possible to prove even a stronger result. I won't go into detail in that here because it's slightly more power. But you can show the convergence of the empirical mean itself to the law of the limit process. So what we've done is a simplified version of this. The idea is that we've shown the convergence on our toy model, but you can show something that's stronger, which is the propagation of chaos inside our system. So as I've mentioned, this is called propagation of chaos because the asymptotic independence of the n particle system is equivalent to the weak convergence of the empirical mean. Okay, so to finish off this talk, because I'm precisely on time, I just wanted to mention a few generalizations of these already pretty general mean field models. So as I've mentioned, one of the problems with the mean fields is that you're forced to look at the limit with an infinite number of particles with weak interactions between all the particles. So if you if you're interested in the geometry of the model, you want to introduce some kind of spatial component to the interactions. So one way to do it is to introduce a kernel of spatial dependence in the term of interaction. So instead of having just the function b, you introduce some kind of function k with the yi is the spatial localization of the ith particle. So the idea is that the term here, kf yj, represents the spatial dependence between the particles I and j. So now when you look at the limit when n goes to infinity, here's the capital N, sorry. You have to consider both the convergence of the processes xkn as previously to some limit process and the convergence of the empirical mean of the particles to some kind of limit distribution to be able to go to take the limit here. So this is one way. And another way is what I've talked about almost a year ago, which is what I've been working on, which is replica mean field models. So another way to preserve the geometry of the n-particle system is instead of looking at the limit when the number of particles goes to infinity, you take m replicas of the initial particle system and you transform the way that interactions happen inside your system. Instead of your interactions happening inside the initial particle system or inside the replicas, basically all the interactions become uniformly routed in between the replicas. So if you have particle I that would interact with particle j in one replica, instead it chooses a replica at random and it interacts with particle j in that replica. And you look at the limit when the number of replicas goes to infinity. And so, of course, if you look at one typical replica, inside of it, you will have some kind of limit dynamics, but you will still have only n particles. So you preserve the initial geometry of the model. So this is just it's just sort of to go around the circle. So now we've come full circle. We started a year ago. Now we've come back to replica mean field models. And so I hope that this talk was a way for you to understand at least the ideas behind what is a mean field model, why do we work with mean field models, and what kind of questions do we want to answer in mean field theory. And so if you're interested in this topic, so I'll just give you two references. So which is basically what I've used to prepare this talk. There's a sort of also a sort of an introductory review by Julien Chevalier, which is kind of simplified, which is where I've taken the Toy model from. And the main reference in the topic is, of course, a course by Alain Sol-Sznitman on the statistical topic and propagations of chaos. And so just a final remark before I conclude and answer any questions that you might have, is that all of the models we've considered here are just a very specific subset of mean field models in general. We've just been looking at models in continuous time, which do with diffusion, with just some kind of Brownian noise. And of course, the mean field models are much more general than that. You can have many, many, many different other stochastic differential equations. But the idea is that you always want to answer the same questions, which is you have some parameter that you're making go to infinity to simplify your model. So you're interested in so you have some kind of limits, stochastic differential equations, and the questions you're interested in are all the limit equations well posed, and does your initial model converge to the limit model? So this is even though the model itself is quite specific, the ideas behind are very general. And so this concludes my talk.
Thank you very much, Michel. Are there any remaining questions?
So it's a very simple question for me. Could you give a concrete example of problems where these techniques is well suited?
Well, So concrete, well, the concrete example I think of immediately is neuron models in neuroscience, where each particle is a neuron, and so if you look at the equations here, you model you model the interactions. You model the interactions with so some kind of potential here. So you can use it also. You can look at it as in game theory. In game theory also, if you look at the process as for instance, you have some as soon as you have some kind of network with different states, and you look at the states as your objects of interest. So your empirical measure here will kind of represent. If you look at, you can sort of introduce the proportion of time that you spent in each state, and express that as the xkn. And so the empirical measure will represent the sort of the mean state of the system. And so for looking at equilibria in game theory, there's a whole theory which is called mean field games, which basically uses models like these, I think. Well, of course, not with this particular randomness, of course, but still you express things in terms of measures, in terms of the empirical mean, and in terms of an occupancy measure, which is like what proportion of the time do you spend in a certain state, for instance. And there are many other applications. The ones that I'm most familiar with, it's much used in mathematical physics as well, because there's if you want, there's I haven't cited it, I haven't put it in the references because I had trouble figuring exactly how to cite it, but there's a master's level course by Cédric Villani where he talks about mean field models, which I've actually used to prepare this talk, where he doesn't come to the topic not really from a probabilistic point of view. He just uses probability theory as a tool, but where he looks at the behavior of physical systems. So he has some Hamilton equations, etc., for which he introduces mean field models, which are more suited to the task. So I hope this. So if you look at, for instance, if your particles are actual physical particles, and you have some physical interactions between them, like attraction, or if you're submitted to some kind of potential, for instance, well, you have a system of n differential equations. You can associate stochastic differential equations to them under certain circumstances, and then, of course, you have a mean field model associated with them.
So if I take your example, assuming that you have, say, n particles which attract each other's, what does compute the mean field? This is the final position of all those particles, or
no? Computing the mean field gives you. You can see it as a caricature, even though I know François likes this term, but others do not. Because the idea is that you have a sort of different model that is a simplified version of your initial model, but it still kind of behaves in a similar fashion. So this is what I've called the macroscopic model. Is the idea is that you have a sort of a statistical description of your system, because instead of having just n particles, you have an infinite number of particles, and instead you're looking at the states that there's sort of a statistical distribution of the states that the particles are in. So maybe it's even clearer in the case of populations of neurons, where the mean field model is just the behavior when you have an infinite number of particles that weakly interact with one another.
And once you have this caricatural model, what can you compute quite accurately? So
For instance,
if I take my example of particle interacting each other.
Yeah. So, well, in that case, you'll be able to compute. For instance, you'll be able to compute. Well, depends on the model, of course, but you'll often be able to compute the asymptotic behavior when t goes to infinity, the proportions of the time that you spend in each state, stuff like that. So mean firing rates of the for in the case of neuron, if in the case of neurons, you'll be able to compute. Well, yeah, basically the proportion of the time you spend in each state. So you have a statistical description of the limit model.
Okay.
Marco, another very interesting instance is this power of two things in scheduling, which is more if you go in the queuing direction. So it all comes from the Russian school. It's Vedenskaya, but it's not popular under the name power of two. Rather, you have a large number of queues, and rather than going to picking one at random, you pick the best among two. And then you work out a mean field. If you you pick two at random, so there is a mean field model. And Vedenskaya and others, and the people who develop this power of two, they look at the response time in these queues. You take the smallest workload among two, and they show that you move from an exponential tail to a sub-exponential tail, for instance, and they compute this delay. So it's very concrete in queuing and scheduling, and it was in the Russians, in the school of Doboshin, they were very active in these things, which are the use of mean fields in networks in our sense, right? Namely scheduling, queuing, communication. I mean, this Bianchi model also for representing CSMA-CA. So there are lots of incarnations in our domains of communication networks, queuing, scheduling, data centers. Srikant has lots of works on these functions at UIUC. These variants about the power of two things for data centers.
Okay.
So it's in terms, and the key thing, as Michel said, is that it's I call it a caricature, but this caricature is computable, right? And it's asymptotically tight, and people study a lot on how far you are when you have say a large system, or how far you are from the limit and things of this type. So it's like what physicists do. It's very it's handy, right? But usually these simplifications lead to either a Makin-Vlasov type equation or an integral equation, a fixed point equation, and you get things which are initially intractable, and suddenly they become very simple.
But it was precisely my point. I guess that it is used if so many scientists talk about mean field, and so I wanted to understand for which kind of problems you can apply it. And but thank you for all those examples.
I have another question.
Yes.
It seems that in the toy model there are infinitely many fixed points, because in the Ornstein-Uhlenbeck solution you can shift it by a translation and you get another solution.
But you have a fixed initial condition, no? That prevents the translation, no?
For every particle you have an initial condition, so you shift the initial condition as well. Am I right?
Well, let me think, because what do you call do you mean that compared to what I've said in the first part, you do no longer have unicity of the fixed point.
Would you please bring the equation of the toy model?
Yes, of course. Here. Yes, here. Here we have both the initial and the ones at the limit.
Not this one. Maybe the previous one.
This one.
Yes.
This is the same one.
Oh, this is the finite n model, but the limiting.
Yes, the limiting is this one.
This one, yes. Here.
So yeah, I haven't gone into detail, but you can. The idea is that when you can rewrite it under you can rewrite it as a linear stochastic differential equation.
As I understood, you should find a solution of this equation for every initial condition. Almost every.
Yes.
So if you shift all of the initial conditions and all of the solutions, you get another solution here.
Well, and why would this be problematic exactly?
Because yes, you think about having a fixed point.
Well, wait. Let me think a second. No, but what we've shown previously, you still have so you can still rewrite this equation as wait, can I where is it that? Where is that? Yes. It's still just a particular case of this. So what we've shown previously will still apply here. You'll still have given an initial condition, you will still have only one solution to this equation.
Yes, given initial condition, yes, you're right.
So and this is exactly since our probability space here. Where is that? Here. It includes the initial conditions, so they're part of what we're coupling on. So they have a very so we're in some sense we're all that we're doing it based on some initial conditions. Does that answer your question?
So I think it's still you defined a map that assigns to every measure m the solution of the equation. I don't know which.
Yes.
So this map here has infinitely fixed points, which are translations of Ornstein-Uhlenbeck process.
No, I don't think so. Because so if you take this process, you if you take the mean here, if you know it's equal to m0.
Would you so the slide that you defined the map?
Yeah, sure. The map is defined here. Wait. Here. So to the map to a measure m, you associate the law of the solution of the SDE. It has already a fixed initial condition.
Oh,
so it's not the process Z. It's fixed.
What is it? This x bar of 0 in the toy model?
In the toy model is going to be y here. It's going to be here yk of 0. It's fixed. If you look at the time here, it's xk of 0 here. This is fixed. It's in no. It has a certain distribution. Usually they're taken iid over k. Oh, the xk is of 0, but so their law is fixed.
Okay, thank you. I will think more about this.
Okay. Oh, so